dimensional space would look like. Okay, so this video kind of tells us how living in two-dimensional space would look like. It's based on Flatland. Flatland is a book, and here Carl Sagan is talking about that.
Let's imagine that we are perfectly flat. I mean, absolutely flat, and that we live, appropriately enough, in a flatland, a land.
Do you also have the audio of the video? Do you hear it too?
Yes.
Thank you.
And designed and named by Edwin Abbott, a Shakespearean scholar who lived in Victorian England. Everybody in Flatland is, of course, exceptionally flat. We have squares, circles, triangles, and we all scurry about, and we can go into our houses and do our flat business. Now, we have width and length, but no height at all. Now, these little cutouts have some little height, but let's ignore that. Let's imagine that these are absolutely flat. That being the case, we know, us Flatlanders, about left-right, and we know about forward-back, but we have never heard of up-down. Let us imagine that into Flatland, hovering above it, comes a strange three-dimensional creature which, oddly enough, looks like an apple. And the three-dimensional creature sees an attractive, congenial-looking square, watches it enter its house, and decides in a gesture of interdimensional amity to say hello. Hello, says the three-dimensional creature. How are you? I am a visitor from the third dimension. Well, the poor square looks around his closed house, sees no one there, and what's more, has witnessed a greeting coming from his insides, a voice from within. He surely is getting a little worried about his sanity. The three-dimensional creature is unhappy about being considered a psychological aberration, and so he descends to actually enter Flatland. Now, a three-dimensional creature exists in Flatland only partially. Only a plane, a cross-section through him can be seen. So when the three-dimensional creature first reaches Flatland, it's only the points of contact which can be seen. And as the apple were to descend through, slither by Flatland, we would progressively see higher and higher slices. So the square, as time goes on, sees a set of objects mysteriously appear from nowhere and inside a closed room and change their shape dramatically. His only conclusion could be that he's gone bonkers. Well, the apple might be a little annoyed at this conclusion, and so, not such a friendly gesture from dimension to dimension, makes a contact with the square from below and sends our flat creature fluttering and spinning above Flatland. At first, the square has no idea what's happening. He's terribly confused. This is utterly outside his experience. But after a while, he comes to realize that he is seeing inside closed rooms in Flatland. He is looking inside his fellow flat creatures. He is seeing Flatland from a perspective no one has ever seen it before, to his knowledge. Getting into another dimension provides as an incidental benefit a kind of X-ray vision. Now our flat creature slowly descends to the surface, and his friends rush up to see him. From their point of view, he has mysteriously appeared from nowhere. He hasn't walked from somewhere else. He's come from some other place. They say, for heaven's sake, what's happened to you? And the poor square has to say, well, I was in some other mystic dimension called up. And they will pat him on his side and comfort him, or else they'll ask, well, show us, where is that third dimension? Point to it. And the poor square will be unable to comply.
Okay, let's go back. So it was just the drawings here, I think they were pretty good in showing how does a two-dimensional space look like for the people living inside two-dimensional space. That doesn't exist, but we can think about that. So just for a moment, assume we have these two-dimensional world. So there is a world which is two-dimensional, and everything there is flat. So let's say we have a human there. A human would look like this, whatever. And the strange thing is that if we have a flat being, living there for them would be very hard, because assume these flat creatures, they want to eat something. So if this flat person wants to eat something, well, as we know, in two-dimensional space, he can't, this thing, this food, can't go inside because there is a barrier there. There is an obstruction here. He should open his mouth. So how is it going to look like? He should open his mouth. So this thing would go inside. But it's not enough, you know, it's not still inside. He wants to eat it. So it should continue to make his mouth bigger so the food would go inside. And if you continue this picture, you understand if something two-dimensional wants to eat something, it should start to deform. And if you continue that, what happens at the end is that this person here will become disconnected. It becomes like this. It's part of him, if it's the other part of him, and the food will come out. There, if the food wants to go in and come out, it would make the person disconnected. So eating actually is something which wouldn't happen, for example, in two-dimensional space. There is no eating in two-dimensional space. You can only eat at least in three-dimensional space. If you want to eat something in two-dimensional space, you should cut the person in half and make that person, well, you could make it kind of disconnected. You should cut the person in half, which is quite strange. Okay, anyway, let's continue. Let's continue with our two-dimensional space. So I mentioned the Pythagorean theorem, which says if you have a right triangle with sides A, B, C, C squared is A squared plus B squared. I mentioned we can use this theorem to compute the length of vectors. So if we have a vector, let's see another example, connecting a point P with coordinates 1 and 3. And we have another point Q with coordinates 4 and 1. If we consider the vector connecting them, PQ, this vector is going to be Q minus P. And Q is 4 and 1 minus P. P is 1 and 3. And the result is 4 minus 1, which is 3, 4 minus 1. And 1 minus 3 is minus 2. Note that when I'm subtracting P from Q, I subtract the first component from the first component, 4 minus 1, and the second component from the second component. So we say the algebra here is component-wise. If we add or we subtract, we add the first component to first component. Or if we are subtracting first component from the first component and second component from the second component. Okay, I would answer that question shortly. So here we have a triangle, right? And this side goes from 1 to 4, so its length is 3. This side goes from 1 to 3, so its length is 2. So here A is 2, B is 3, and we are looking for C. C squared is 3 squared plus 2 squared. So C here is the square root of 13. That's how we use the Pythagorean theorem to compute the length of vectors. Okay, there's a question here which is asking, Mariam is asking, what is Q minus P? What do vector coordinates represent? So first of all, let's see what does these coordinates represent. So let's look at the previous question one more time. If I have a point P with coordinates, say 1 and 4, and another point Q with coordinates 2 and 3, P is 1 and 4. So P is here. And Q is 2 and 3. So maybe 2 and 3 is not good. Let's choose something slightly larger, more interesting. Let's say 4 and 1. So Q is 4 and 1, Q is here. Now, if you look at PQ, which I said it is Q minus P, what we would get is 4 and 1 minus 1 and 4, right? 4 minus 1 is 3, 1 minus 4 is minus 3. So this vector PQ would be 3 and minus 3. What does these numbers present? Look at the vector P and Q. I can say the vector PQ goes forward by 3. This length is 3, right? Goes forward by 3. That's what the first component presents. And then it goes down by 3. Because it goes down by 3, that's what this component presents. So these numbers here, the first coordinates, the first component, which is the x component, and the second component, which is the y component, tell you the displacement of this vector. This vector in the x direction goes forward by 3. In the y direction, it goes down by 3. Does that make sense? Did I answer your question, Mariam? Okay, good. Okay, so Pythagorean theorem tells us about the length of vectors. But there is another thing about the vectors which is also important. When we have a vector, its length is one important quantity. There's another important quantity, and that's slope of the vector. So if you have a vector, again, let's look at vector. Suppose P is a point equals 0 and 0, and Q is another point, say it's here. The coordinates are 1, 2, 3, and the y component is 1, 2. If I look at this vector connecting them, I would get PQ, which is Q minus P, and that's 3 and 2, minus 0, 0, which is 3 and 2. Well, I can compute its length now. I know how to compute its length. I use Pythagorean theorem. Now there's another thing which is also important, and it's the slope of this vector PQ. The slope of this vector, I would tell you first how we compute it, and then I would tell you what does this thing mean. So PQ is connecting this point to this point, right? The slope would be, it means this. Look at the second components. Here, the second component is 2. Here, the second component is 0. Right, subtract them, 2 minus 0. Now look at the first components. Here I have 3, here I have 0. Subtract them, 3 minus 0, and divide them, 2 over 3. That's the slope of this vector. Let's compute it for another vector too, and then I would tell you what does this thing mean. So let's look at another vector. Suppose we have a vector connecting a point P, which its coordinates are 3 and 2, and we have another point Q, which its coordinates are 5 and 4. And this is PQ, the vector connecting them. The slope of PQ means, okay, look at the y coordinates. Here I have 4, here I have 2. Subtract them. I would get 4 minus 2. The second one from the first one, 4 minus 2. Look at the first coordinates, 5 and 3. Subtract them, 5 minus 3. I would get 2 over 2 is 1. The slope of PQ is equal to 1. Okay, are we clear on computing that? That's the first thing. We want to first know how to compute this. Okay, if there is no question, let's go on and see what does this thing mean. So if I have a vector PQ like this, it has some slope. I might have another vector like this, P prime, Q prime, and another vector like this. Let's show this with P second and Q second. I have 3 vectors here. Now, suppose I have 3 other vectors. I use another color, say A, B. And there is another vector, A, B. The first thing to note about these 4 vectors is that these 2 vectors, they kind of go upward, right? These 2 vectors, they kind of go up. This vector is horizontal. And this one goes down, up, horizontal, and this one goes down. Now, the slope of these vectors are going to be positive because they go up. The slope of this vector is going to be 0 because it's horizontal. And this one which goes down, its slope is going to be negative. Let's check that. So if we have a vector connecting the point P1 and 1 to another point Q3 and 3, the slope of this vector is going to be, okay, the points are 3 and 3 and 1 and 1. It's going to be 3 minus 1 over 3 minus 1, which is 2 over 2, which is 1. This is a positive number, right? Now, look at another vector, a vector which goes down. Suppose we have a point P, which its coordinates are 1 and 3, and another vector, another point Q, which the coordinates of Q are 2 and 1, right? Now I can connect them. I would get the vector PQ. I want to see what is the slope of PQ. Okay. I should subtract the second coordinates. It's going to be 1 minus 3, and then I should divide it by 2 minus 1. Now 1 minus 3 is minus 2, 2 minus 1 is 1, anything over 1, minus 2 over 1 is minus 2. So it's negative. So you see, if the vector goes upward, the slope is going to be a positive number. If it goes downward, it goes down, it's going to be a negative number. If it's horizontal, say the point P is 1 and 1, and the point Q is, say, 3 and 1. So this is 1 and 1, this is 3 and 1. If I connect them using a vector, this is horizontal. If I look at the slope, it's going to be, I should subtract the second numbers, which is going to be 1 minus 1, and then divide it by first components, 3 minus 1, which is going to be 0 over 2. 0 over any number is 0. So let's summarize. If we have a vector which goes upward, the slope is going to be positive. If it's horizontal, slope is going to be 0. If it goes downward, the slope is going to be negative. Now, there is another case. There is another interesting case, and that's the case where the vector is vertical, like this. What is the slope? Does anyone know what is the slope when the vector is vertical? Well, yeah, that is correct. So suppose this point P is 1, 2, 3, and yeah, both of you are correct. So suppose it's 3 and 1, it's P, and then it's Q. Q is 3 and, say, 4. This is vertical, right? So P is 3 and 1, and Q is 3 and 4. If we compute the slope of PQ, we should subtract the second coordinates, which is 4 minus 1. We should subtract the first coordinates, which is 3 and 3. We get 3 over 0. That is very important. That's one of the most important things in math. You can't divide by 0. You can't divide by 0. It is not defined. Not defined. Some people might also say infinity. At this stage, it doesn't matter. I prefer you to say it's not defined. Although in some sense, you can say the slope of this vector is infinity because, you know, the slope of vertical thing is 0. As you try to shift this, try to move this vector, the slope becomes more and more. You see these vectors, they have more and more slope until you get to vertical one, which in some sense its slope is infinity. So either infinity or not defined. So if you have a horizontal vector, slope is 0. If you have a vector which goes up, slope is positive number. If you have a vector which goes down, the slope is a negative number. If you have a vertical vector, the slope is not defined. Okay. Or DNE, depending on what notation you use, or infinity. Okay, is there a question? We will eventually get to 3D vectors. Yeah, we will. We will even get to higher vectors. That is true. Okay, so that's the case here. We have all these different vectors. Now we have, so we are assigning two things to a vector. We are assigning length and slope. Now there's one more thing we want to kind of talk about, and that's the addition of vectors. There are two approaches here. One approach is the algebraic approach. What does this thing mean? It means if you have two vectors, let's say we have a vector PQ, which has some coordinates, anything, say 2 and 3. And another vector AB, which has some coordinates, let's say 3 and 5. We can add these vectors. We can look at AB plus PQ. And the addition is component-wise. We add 2 to 3, we get 5. We add 3 to 5, we get 8. 5 and 8. And that's the addition of these two vectors. As simple as that. But there is another approach, which is the geometric approach. Okay, say we have two vectors. This is one vector, PQ. This is another vector, AB, okay? And I want to add PQ to AB. I want to see what is the sum of PQ and AB. The first thing is that I am allowed to move vectors around. Not only me, also you. So we are allowed to move vectors around. So I'm around to move AB to here, but just move it. I should keep it parallel. The slope and the length shouldn't change. Or I'm allowed to move the vector. So I'm allowed to move it here, or I am allowed to move it here, as long as I keep it parallel and I keep it the same length. Okay, so you can think about it as a piece, as a segment, which you are allowed to move it around, but the key point is that it should stay parallel and the length shouldn't change. Okay. Now that we are allowed to move them around, what I'm going to do is that I'm going to move it to the point which it has the same initial point, same start point as the other vector PQ. So I would move AB here. See, I would just move it there because I'm allowed to move it anywhere. I would move it there. So they would have the same starting points. Okay. Now the idea is that from this point, let me use colors, from this green point here, I would draw a line, a vector parallel to PQ. So this is PQ, I would draw something parallel to that. I hope it's really parallel. Something like this. With the same size. So exactly parallel to that. And then from the red point, I draw something parallel to AB. So parallel to AB, I would draw something with the same size. They would get to a point, these two new vectors, they end up at same point. Now, if I connect P, let's call that point C. If I connect P to that point C, we get a new vector, a blue vector. This blue vector, which here connects P to C, is the addition of these two vectors. Okay, so let me explain one more time. So I have two vectors. Let's say one of them is here, PQ. The other one is here. This time, let's change the direction. Let's say the other one is here, AB. And I am looking for PQ, this vector, plus AB, the other vector. How can I compute that geometrically? What I should do is I should move one of them, doesn't matter which one, I should move one of them. Here I would move the blue vector in a parallel way such that these two vectors, they have the same starting point. So I move this one here. I would keep it parallel. I wouldn't change the length. Okay, I would now remove the previous vector. When they have the same starting point, from these 2 points, these two red points, I draw two vectors, each of them parallel to the other one. So from Q, I would draw a vector parallel to the blue one, From the other red point, I draw another vector parallel to the black one. They would end up at the same point at some point. There would be an intersection point. Let's call that C. I would connect P to C. Let's use another color. This vector PC is the sum of PQ and AB. Okay, so now if they ask us, if they tell us PQ is 1 and 2 and AB is 2 and 3, what is PQ plus AB? There are two ways to compute this. The first way is so-called the algebraic way, is just by adding them. I have 1 here, I have 2 here, 1 plus 2 is 3. I have 2, the second components are 2 and 3, 2 plus 3 is 5. That's it. That's one way, that's the algebraic way. There is also the geometric way. Geometric way means draw these vectors in the plane. Okay, the first vector is 1 and 2. It means if I can start both of them from the origin, it doesn't matter where you start. We can start from this point. This point is called the origin, 0 and 0. This vector P and Q, the first coordinate is 1, it goes to right by 1, and the second coordinate is 2, so it goes up by 2. So the first vector PQ, I can present it with this vector. The other vector is, the coordinates are 2 and 3. The first coordinate is 2, the second coordinate is 3. I can present the second vector like this. Now I can do this trick. I can, from these two red points, I can draw two vectors parallel to the other one. From here, I would draw a vector parallel to the blue one. And from the other vector, I would draw a vector parallel to the black one. It would get to a point. And then I would connect this origin to that intersection point. And this is the sum. This green thing is the sum. Okay, so this is 3 and 5 is the algebraic way to find it, and the geometric way is with this algorithm. Okay, any question here? Yeah, this is the sum of displacement. You are completely right. There's another way of doing it, and maybe that would answer your question even better. If you have two vectors P and Q and A and B, in order to compute their sum, one way is, as I said, to put them next to each other and then do this trick, which I did. The other way is to use what is called tip-tail or something like that, which means if I have PQ, I can move AB, bring the beginning of A, bring A here, and put AB here. And then if you connect the beginning point to the final point, that's also the sum. That's the third way to compute this sum. All of these ways are equivalent. You can do any one you want. Yes, I can also add the individual X and Y components. That's actually what I call the algebraic way. So as you can see, if maybe I should express this more carefully. So if I have two vectors, PQ and AB, what I can do is I can keep one of them in its place, say PQ, and move AB here. I shouldn't write the points A and B anymore. Anyway, And then draw these parallel lines to get to some intersection point and connect P to that point. That's one way of adding them. The other way of adding them is let PQ be here. Rather than moving AB to this point, we can move AB to Q. So I can bring AB here. And then I can connect P to the final point. And if you compare these two cases, you can see the sum is the same thing. So it doesn't matter which technique you use, you would end up with the same answer. This is called parallelogram method or technique or whatever. I think this is called tip-tail, something like that. Both of them are correct, or you can just add them component-wise, as I mentioned earlier. Just add them. Okay, any question? Okay, good. So, okay, so let's continue. Now, there is one more thing, and that's when we have a vector, say this is a vector, let's show it with PQ. We can multiply vectors by numbers. I can multiply it by 2, for example. What is 2 PQ? It means vector in the same direction, which its size, it's twice P and Q. So it would be, this would be the result, 2 times PQ, right? It's just a vector in the same direction, but its length, it's 2 times PQ. So for example, if I have another vector like this, I don't need to use letters like PQ for vectors. I can use one vector too. A lot of times we show vectors with just V, because V is it's the initial for vector. So for example, 3 times V means we have a vector in the same direction, but its length is 3 times V. Now, one important thing is that, first of all, if we have a vector V, 1 times V is equal to the V itself. Doesn't change anything. 0 times V is going to be 0. It's a vector which its length is 0. Remember, 0 times anything is 0. So even if you multiply a vector by 0, you would get 0. And the vector 0 is this. This is a vector. But the length of this vector is also 0. So it's a vector of no displacement. So if we show displacement of an object with a vector, if you don't move the object, the vector which shows its displacement is this vector. It's a 0 vector. And one more interesting case is when we are multiplying a vector by a negative number. So if we have a vector V here, minus V, which is -1 times V, is a vector with the same length in the opposite direction. This is minus V. Okay. And if we have a vector V, -2 times V is a vector in the opposite direction, but the size is actually 2 times V. It's going to look like this. So this is -2V. Actually, the question is, so you only multiply the magnitude and not components? Actually, we are multiplying the components. So, okay, let me give further details on that. If I have a vector V, which its coordinates are 1 and 1, this is 1, this is 1, I can show this vector with this, right? This is a vector. I want to show 2 times V. This is 2 times V, same direction, but the magnitude is, the length is 2 times V. Now, if I look at the coordinates of this vector, is actually the coordinates are 2 and 2. That is true. I'm just multiplying every coordinate by 2. So if, for example, if I have another vector, say u, I show it with u now, with one, which the coordinates are 1 and 3. The coordinates are 1 and 3. This vector looks like this. If they ask me what is 2 times u, that's going to be this vector. What are the coordinates of this vector? If you look, you would see the coordinates are 2 and 6, which exactly means I am multiplying the coordinates by 2. So we really don't need to draw every time. So if you have another vector, so interchangeably, I sometimes use PQ for the vectors, sometimes V, sometimes U. The reason I'm doing is that the book is also using all these different notations. I want you to get used to these things. It really doesn't matter what notation you use. When we use, PQ, when we use PQ, it means it's a vector connecting P to Q. When I use V, it means I don't really care about those vectors. Those points, I just care about the vector itself. So, so if V is anything, is like 1 and 3. So for example, if they ask me what is minus 2V, I should multiply each coordinate by minus 2. So that would be the vector. There is a question, let me see. Minus 2V and minus V do not include the original vector. Yeah, I mean, including is not the correct word. What you have in mind, your tuition is not correct, but we don't usually say the vectors include each other. Even if I have V here, I have 2V here, I wouldn't say this vector include the other one, but your intuition is correct. If I look at minus V, it's completely in the opposite direction. Yeah. So, and also if I look at 0 times V, it means 0 times 1, which is 0, 0 times 3, which is 0. So, and that's the 0 vector, which is just a point. So whenever I have a number here, I multiply both of the components with that number. I would multiply minus 2 by 1, the result is minus 2. I would multiply minus 2 by 3, the result is minus 6. Okay, that's how to do this multiplication. This multiplication, remember, we are multiplying a number and a vector. So we are multiplying a vector by a number. This is multiplication where one of them here, minus 2, for example, is a number, and the other one, V, is a vector. And the result is a vector. The result is not a number. This result, minus 2 and minus 6, is a vector. So we multiply a vector by a number, we get a new vector. Okay, so we can add vectors together. We can add vectors together. We can subtract vectors. We said P minus Q. We subtracted points. We can subtract the vectors too. So if V is say 2 and 3, and U another vector is 1 and 4, we can subtract these two vectors. V minus U is just 2 minus 3 minus 1, 4. It's just like the points, because in reality, there's really no difference. We just subtract them. We can add them. V plus U is, we add the first coordinates, 2 and 1, the sum is 3, 3 and 4, the sum is 7. And we can multiply vectors by a number. 2 times V would be 2 times 2, which is 4, and 2 times 3, which is 6. So we can add, we can subtract, and we can multiply the vectors by numbers. And yeah, that's it. So yeah, so we can do these algebraic things. Okay. Now let's go to the next notion. The next thing I want to talk about is a unit vector. A unit vector in direction of another vector, of a vector V. Suppose a vector V is given. Okay, I have a vector V. This is a vector. The length of this vector, I can compute its length using Pythagorean theorem. It's a number. It might not be 1. Sometimes I'm interested a vector in direction of v, but a unit vector. Unit vector means a new vector u, which u and v, they have the same direction. But u has length 1. It's called unit vector. Yeah, break in 4 minutes. So just stay with me for 4 more minutes and then we would have a break, okay? So u is a vector in direction of v, but its length is 1. What is that vector? Actually, that vector is this. Look at v and compute its length. I can, if the length is a non-zero number, I can look at 1 over the length of v. It's also a number, and I can multiply that number by v. Okay, don't get confused. Let's look at one example. Let's see. Let's say we have a vector v with coordinates 3 and 4. Okay, that's v. So we want to answer this question. Find u. What is u? Unit vector in the direction of v. Okay, what is the length of v? I want to see what is the length of v. I should use Pythagorean theorem. So the length of this side is 3. The length of the other side is 4. I named the length of v to be c. Pythagorean theorem tells us c squared is 3 squared plus 4 squared, which is 9 plus 16, which is 25. Yeah, that's a special triangle. So c squared is 25. Therefore, c is 5. The length of v is 5. Now, the unit vector in direction of v means you should look at v and divide it by that number. Fine. What does dividing mean? It means we should divide each component by 5. So the first component was 3. Now the first component will be 3 over 5. The second component was 4. Now the second component will be 4 over 5. This vector u is actually, I draw it with blue color. It's going to be actually in direction of v. It goes up to 3 over 5, which is less than 1. And the other coordinates is 4 over 5, less than 1. If you use Pythagorean theorem for this blue one, you would see the length of this one is 1. So we get a vector with length 1 in the direction of v. Okay, let's just do one more and then we would have a break. So let's say we have another vector v, which is the coordinates are -1 and 3. Okay, the first one is the x coordinate, -1 is here, 1, 2, 3. That's how the vector looks like, -1 and 3. We should compute the coordinates of, we should compute the length of v. We use Pythagorean theorem. I make this right triangle. This length is 1. Remember, the length is a positive number. Although this coordinate here is -1, but the length is always a positive number. Length is the positive number measuring that side. And the other length is 3. And if I call this length c, Pythagorean theorem says c squared is 1 squared plus 3 squared, which is 9 plus 1 is 10. C is the square root of 10. So the length of v is the square root of 10. Now, what is the unit vector in direction of v? It means you should look at v and divide it by its length. So, and we should do that component wise. We would divide -1 by square root of 10, and then we divide 3 by square root of 10. So V would be something almost like this. It would be U. Something in direction of V with length 1. Okay, let's have a break. We will come back in 10 minutes, in 15 minutes, 11:20. Okay? So if there is no question. Yeah.
Sorry, I'm confused about what does U represent?
Well, you know, sometimes we are using vectors to just show a direction. We are not interested in the length. Here, U represents the direction, but the length is always 1. We will use that later, actually. We will use it in a lot of places. But the thing we need to understand now is that if we have a vector and if the length is not 1, we can divide that vector by its length to get a vector in the same direction, but it's a unit vector. The length is not something arbitrary. So if you look at U now, if I ask you what is the length of U, if you compute the length of U using Pythagorean theorem, you have this small triangle here. I would draw it here. It is U. One side is 1 over square root of 10. The other side is 3 over square root of 10, right? So if I call the other side C, Pythagorean theorem says C squared is 3 over square root of 10 squared plus 1 over square root of 10 squared. The first one is 3 squared is 9. Square root of 10 squared is 10 plus. And the second one is 1 over 10. 9 plus 1 is 10. 10 over 10 is 1. So C squared is 1. It means C is 1, which means the length of U
So basically,
yeah.
So it's just the direction of the vector with the length equal to 1.
Yes, that is true. It's the direction of the
Thank
vector
you.
with the length equal to 1. That is correct. Yes.
Okay. Thank you.
Yeah, you're welcome. So let's have a short break and I will come back. Is V a point? Okay, let me stop recording and I will answer these questions.